Hi everyone. So this video will present an example for backpropagating a convolutional layer. And this is an example of a two-dimensional, let's say a two-dimensional image or a two-dimensional input that has more than one channel. So an example is a color two-dimensional image. So basically you have the two dimensions of the image, and then you have RGB, red, green, and blue. They correspond to three different channels. And the goal of this example is really not to introduce a new concept, but rather to appreciate, to walk through the example, to appreciate the amount of computation that is needed for backpropagating a convolutional layer, and that will also help us appreciate how much convolution is saving in terms of computation in comparison to a fully connected layer. And it also can shed light and makes you think and get curious about the parallel computation opportunities, which could be a scope of a whole separate course, like on graphical processing architectures and how to parallelize matrix multiplications or tensor operations that are involved in both the forward propagation and backward propagation of deep neural networks. Also, one thing to note when considering that example is that if you have a mini batch, which is typically what's done, if you're processing a mini batch of examples, then that will add another dimension, right? So here this is just for processing a single training example. Now, if you want to see or to appreciate the computations in the general multidimensional case, then you might want to look at this report, technical report, which is available online, called Multidimensional Downsampled Convolution for Autoencoders. Now, let's go to our 2D single example, right? So not many batch, just a single example. So let's say my output, right, has multiple channels and the input has multiple channels. So let's call the output Zijk, where I is the output channel index and Jk is the image, right? So if the RGB is the input, basically, for the case of an RGB image, then if the output also is an RGB image, then I will range between three values and J and K will range over the two-dimensional over the two dimensions of the image. Now, so that output, right, as a function of the kernel K and the input V and the stride S, right? So this is convolution with a stride. S could be one to remove the stride. This is a sum. So every output pixel or every output point, right, corresponding to one of the channels, one of the values for both the two dimensions, right? This is a sum. So this is the forward propagation. We're not talking about backward propagation yet. Sum over all input channels, right? So remember, if I have that example of two-dimensional images with multiple channels, then the kernel is also two-dimensional. Let's say 5 by 5, so it will range from -2 to 2. The offset of the kernel will range from -2 to 2, right? So -2, -1, 0, 1, 2 in both dimensions. So this is a 5 by 5 kernel, for example. In that case, the M and the N will range from -2 to 2. And also the kernel is over the multiple dimensions, right? So the output, for example, for the third dimension, right, point number 5 and 5, will depend on all the input channels, right, the neighboring pixels in all the input channels, right? So the kernel itself is multidimensional, and the dimensions of the kernel or the number of channels in the kernel will depend on basically the number of channels in the input, right? So we sum over the channels in the input channel indices, the row and the column offset of the basically of the kernel, right? So here the K value here depends on M and N, right? So this is the kernel value for the m row, for a row offset equal m, and the kernel value for a column offset equal n, and between an output channel I and an input channel L. And V is the input here, L is the channel index of the input, and then j minus 1 times S, because we shift by a stride. If S equal 1, then it's just j minus 1 plus m. So it's just the index of the output pixel, right, in the first dimension, plus the row offset. And here the index of k minus 1 times S, if S equal 1, then it's just the index of the output value in the second dimension, of the output pixel in the second dimension, plus the column offset, right? If there is a stride, then we jump by the stride. So, and the stride, so in that case, in here in this example, the stride is basically the same in both dimensions, which is typical, but keep in mind that the stride could be different in the different dimensions, right? So now let's go, so that was the forward propagation. Let's go to the back propagation. So let's define Gij as the gradient with respect to the output in channel I, output channel I, and the index of j and k in the two dimensions, right? So we start, so remember in backward propagation, we start, when back propagating a layer, you start with the gradient of the cost with respect to the output of this layer, and then you back propagate, right? And then from that gradient, you can compute the gradient with respect to every parameter, and the parameters here are the kernel values, right? And here the kernel has a value. So even for that single example case and the two-dimensional case, where in practice you will typically have multiple examples, which adds a new dimension to the kernel, right? And you might have inputs that are three-dimensional or even higher dimensional. So even for the 2D case, the input is 2D but with multiple channels. The output is 2D with multiple channels. And only a single example, the tensor representing the kernel is 4-dimensional. Because it has an index for the output channel, an index for the input channel, and two indices for the row and column offsets, for the offsets in the two dimensions, right? So to compute the gradient with respect to every kernel value, you basically sum over all possible row and column offsets given by m and n here, right, on the output, right, times on the gradient with respect to the output, right, times the value of the input, right, because the kernel was multiplied by multiple inputs to generate that specific output, right? So so here to compute the kernel, the gradient with respect to a kernel value given by the 4 indices, the output channel index, the input channel index, the row offset, the column offset, we sum over all possible values of the row and column offsets, m and n, and then we have the output at that channel, at the output channel index corresponding to the index in the kernel parameter that we want to compute the gradient with respect to, times, so this is Gimn, and G is basically defines the gradient with respect to the output, right? Times the input at the channel given by the input channel index, and then the row offset multiplied by the stride times. So you can think of m here as the m and n are the dimensions, basically the spanning the two dimensions, right, where the kernel is affecting. So basically that kernel, even for the same output channel, same input channel, will affect multiple positions across the two dimensions. And this is what the m and n are. So to find the index of the input, so basically we span all output pixels that this kernel parameter is affecting, right? So you go to the output channel index I, and then the M and N spanning over all output values in that output channel that the kernel is affecting. And for every value of M and N, to find the input value that the kernel affected, basically you multiply M-1 by the stride, and then you add the offset corresponding, which is the K in the first dimension, corresponding to the index of the kernel parameter. Right, so within the 5x5 kernel, the offset corresponding to that kernel parameter, you add it to the value of the output, right, multiplied by the stride plus that offset, right? So for example, the kernel value in 5x5, the kernel value lying at -1 and 0, if the output index is 5, then the input index should be 4. Right, so you compute the gradient of the output with respect, the gradient of the cost with respect to the output index at 5 and 5, and this is multiplied by the value of the input at 4 and 5, because the kernel value is -1 and 0, right? So basically, it's very easy to get confused about these indices, but the idea is very simple. For every kernel parameter, you want to compute the gradient with respect to this kernel parameter, so you want to know all the output values or all the output pixels or the output parameters that this kernel parameter is affecting. And the indices in the kernel parameter, there are 4 indices in this case. Output channel index, that tells you where in the output to look at. Input channel index, it tells you where in the input to look at. So these I and J, the output channel index and the input channel index, they give you 2D images, right? Or 2D vectors or 2D matrices of the output and the input. And then the offsets, in this case K and L, tell you which output to relate to which input, right? And basically then you compute backpropagation by multiplying through all the values, all the parameters that this kernel parameter is affecting. You multiply the gradient of the cost with respect to the output times the input, right? And so this is the step where you compute the gradient of the cost with respect to the kernel parameters. There is also a step where you compute the gradient of the cost with respect to every input value, right? And there you would basically sum over all kernel parameters that affect this input value times, for every kernel parameter, times the output value, where times the gradient with respect to the output value that corresponding to the output parameter that was multiplied by that kernel to the output that resulted from the multiplication of that kernel with the input parameter, right? So it's I understand it can be confusing. It's confusing for me as well, but the idea is very simple. You start with the gradient of the cost with respect to the output, and then to go to compute the gradient of the cost with respect to the kernel. With any kernel parameter, you see all output parameters that this kernel parameter is affecting, and for every such output parameter, you look for the input parameter with which that kernel parameter that was multiplied to produce that output parameter. And then you need to backpropagate in order to compute the gradients with the layer before, and in order to backpropagate, you compute the gradient with respect to the input of that layer. And this will involve multiplications of the kernel with the gradient with respect to the output. The last comment before we end this video is basically about the bias. It's typically to have one bias per channel of the output. Sounds good? Thank you.